Fine. Today we are going to see about wave propagation in the ionospheric propagation. So in this slide, we introduce ionospheric propagation, also called skywave propagation. In this method, electromagnetic waves are transmitted upward towards the ionosphere instead of directly along the Earth's surface. The ionosphere acts like a bending medium, allowing these waves to return back to Earth over very long distances, even beyond the horizon. This makes it extremely useful for long-distance communication, especially in the high-frequency or HF band. To achieve this, antennas such as V antennas and rhombic antennas are designed to direct their signals upward at suitable angles. The ionospheric region of Earth's upper atmosphere, extending roughly from 60 kilometers to more than 400 kilometers above the surface. It is formed when solar radiation, particularly ultraviolet rays and X-rays, ionize atmospheric gases like nitrogen and oxygen. This ionization creates free electrons and ions. The concentration of these free electrons is very important because it directly influences how radio waves travel through this region. The ionosphere is divided into three main layers: D, E, and F. The D layer is the lowest and mainly absorbs radio waves during the daytime, but it disappears at night. Above, it is the E layer, which reflects some radio signals and is responsible for phenomena like sporadic E propagation. The F layer is the highest and most important for long distance communication. During the day, it splits into F1 and F2 layers, and at the night they merge into a single F layer. When radio waves enter the ionosphere, it encounters regions with different refractive indices due to varying electron densities. Because of this, the wave does not reflect sharply but gradually bends, which is called refraction. If the conditions are right, specifically, if the electron density is high enough and the wave enters at an appropriate angle, the wave bends back towards the Earth, appearing as if it has been reflected. Critical frequency is the maximum frequency that can be transmitted vertically and still return to Earth. If the frequency exceeds this value, the wave passes through the ionosphere and is lost in space. The critical angle, on the other hand, is the maximum angle at which a wave can be transmitted and still return. For high frequencies, the transmission angle must be smaller or more shallow to ensure that the wave bends back to the Earth. Virtual height. It is the apparent height from which a radio wave seems to reflect. In reality, the wave bends gradually, but for simplicity, we assume it travels in a straight line to a certain point and then returns. This imaginary point gives us the virtual height. This concept helps engineers calculate communication distance and understand how far signals can travel. The maximum usable frequency, or MUF, is the highest frequency that can be used for communication between two locations via ionospheric reflection. Operating close to the MUF provides efficient communication with minimal signal loss. However, MUF is not constant. It varies depending on factors such as time of day, season, and solar activity. Skip distance is the minimum distance from the transmitter where the sky wave returns to Earth. Between the end of the ground wave coverage and the start of the sky wave, there is a region where no signal is received. This is called skip zone or dead zone. As the transmission frequency increases, the skip distance also increases, affecting communication coverage. As radio waves travel through the ionosphere, their polarization can rotate due to interaction with the Earth's magnetic field. This effect is known as Faraday rotation. Because of this, the orientation of the received signal may differ from the transmitted one. leading to signal fading. To reduce this effect, circularly polarized antennas such as helical antennas are often used. Finally, the factors affecting propagation is ionospheric propagation is influenced by several factors. Diurnal changes causes differences between day and night conditions, especially due to the presence or absence of the D layer. The solar cycle, which follows an approximately 11-year pattern, affects ionization levels and usable frequencies. Additionally, sudden ionospheric disturbance caused by solar flares can disrupt communication by increasing signal absorption, sometimes leading to complete blackouts. Thank you.